Swayam Prabha. Digital India. Educated India.
Okay, good morning. The topic of this lecture is on packed column distillation. So far we have looked at distillation in a tray column design, but there are some scenarios where a packed column can also be used for distillation. So before we look at the design principle of packed column distillation, let us first understand the types of distillation based on the operating pressure. Okay, so what we are saying is the distillation can be broadly classified into three types of distillation based on the operating pressure. Okay, for example, we call the operation as atmospheric distillation, whenever the operating pressure is between 0.4 to 5.5 atmosphere. Okay, so in the range of 0.4 to 5.5 atmosphere, the distillation is denoted as atmospheric distillation. Whereas when the pressure is less than 0.4 atmosphere, we call them as vacuum distillation. And if the pressure is greater than 5.5 atmosphere, this is called pressure distillation. So among the industrially relevant distillation operations, this atmospheric distillation is the most commonly used. This is most commonly used operation. Now, if you talk about the vacuum distillation, which basically means that we are operating under low pressure, so the main objective of doing vacuum distillation is to reduce the boiling point of the boiling mixtures. For pure components, we know that when we reduce the pressure, the corresponding boiling point also decreases. This is something you can see from Cauchy-Clapeyron equation for a pure component. In the same way, for a binary mixture of A plus B, if you reduce the total pressure or if you operate the distillation at low pressure, the corresponding boiling points will also come down. Okay, so the main motivation for vacuum distillation is to bring down the boiling temperature. So the next question is, why do we want to bring down the boiling temperature? What is the problem with atmospheric or normal boiling point based distillation? Well, there are several reasons for this. At least we can say some three distinct advantages by doing vacuum distillation or low pressure distillation. There are three distinct advantages. One is that you will see that at low pressures, the relative volatility alpha, this basically increases. Okay, so because when we change the pressure, we change the VLE data itself. So it happens so that when we reduce the pressure, operating pressure, the relative volatility or the alpha by notation, this increases. And we know that alpha is related to the ease of separation. When alpha is more, when relative volatility is more, the separation can be also effected very easily. Okay, and you can see this by looking at TXY diagram. Suppose, let's say this is TXY diagram, and you will see that this is TB and this is TA, let's say for some pressure P1. Okay, now when you reduce the pressure, operating pressure, you will see that this curve moves down something like this, where P2 is less than P1. So by reducing the operating pressure, we have achieved two things. One is we have reduced the boiling points of the pure species as well as the mixture, and also if you look at the separation of XY curves, you see that it broadens. Okay, and this can be more clearly seen in the XY diagram. This is the 45-degree line, and if you get this XY diagram for P1, for P2 it would be something like this. Okay, you can see that P2 is much away from the 45-degree line compared to P1, meaning that the relative volatility is now increased when you go to low pressures. Okay, this is coming purely from thermodynamic reasons. Okay, so we can take advantage of the increased relative volatility by operating the distillation column at low pressure. Okay, now what are the things that we can do if the alpha can be increased? For example, what we can say is that for a given separation, the number of theoretical stages this comes down. Okay, so compared to atmospheric distillation, if you do low pressure distillation for the same product quality and flow rates, the number of stages that you need would come down when you operate at vacuum distillation. Okay, so this is one advantage. Let's say you have a fixed number of stages and then you are going from atmospheric pressure to low pressure distillation. In that case, for a fixed n stages, going to vacuum distillation or low pressure distillation would mean that the reflux ratio will come down. Okay, so that means you can actually operate at low liquid flow rate. The reflux ratio relates to the liquid flow rate that is refluxed, so that will come down if you want to fix the number of stages in the atmospheric distillation versus vacuum distillation. Let's say you want to fix both for a fixed number of stages and reflux ratio, going from vacuum atmospheric distillation to vacuum distillation would actually increase the purity. That means XD goes up. So these are all related implications of increasing the alpha or the relative volatility. I can give one specific example. Studies have shown that in the case of nylon 6 manufacturing, there is a particular component that we want to distillate of, the mixture of cyclohexanone plus cyclohexanol. Okay, these are all two components, A plus B. Okay, these are intermediates in the formation of carpolactam and nylon 6 also. So in this case, a study have shown that alpha can be increased from 1.4 to 1.7 when you go from atmospheric distillation to a vacuum distillation. So when you increase this alpha, all these consequences can be exploited. That is, you can operate at low number of stages, or if you have a fixed design already, you can operate at low liquid flow rates, or if you want to keep the number of stages and the flow rate the same, but the purity can be increased. Okay, so these are all consequences of increased relative volatility. Okay, so so this is one of the reasons. The second reason is that sometimes the product at the reboiler may undergo some undesired reactions. Okay, it can decompose, or it can polymerize, or it can undergo some decoloration. Okay, all because of chemical changes. So if you want to avoid that, okay, you are thinking about thermally sensitive materials, thermally sensitive products, and by doing vacuum distillation we can avoid decompositions or polymerization or other chemical changes to the product. Okay, one example can be that in the separation of ethyl benzene plus styrene. So styrene is a monomer, it can also polymerize easily. Okay, so when you try to separate ethyl benzene from styrene in atmospheric distillation, generally it is designed such a way that the reboiler temperature is never more than 106 degrees Celsius. Okay, if you go to higher temperature than this, then the styrene will polymerize and become polystyrene, which is undesired. Okay, this is in atmospheric conditions. But if you choose to do this at vacuum distillation, this temperature actually in one study was brought down to something close to 75 degrees Celsius. Okay, where it's much more safer to avoid the polymerization of styrene. So you can see that vacuum distillation offers this advantage of preventing undesired reactions or decompositions. Third, so when we bring down the boiling point by reducing the pressure, the heat duty for the reboiler will come down. What that means is some low cost heating resources, something like low pressure steam or even hot water is enough to provide the heating duty for the reboiler. You don't have to have any furnace or you don't have to have any high pressure steam. Okay, so use of low cost heating sources. So this means low pressure steam or simply hot water. So all these arguments basically say that there is distinct advantages of using low pressure or vacuum distillation over atmospheric pressure, atmospheric distillation. So the next question is, how about doing this vacuum distillation in a tray column? Okay, so we have to think about choice of distillation apparatus. So one common choice or natural choice is tray columns. And then we also talked about in absorption and stripping that packed column can also give a good contact between the gas liquid phases. So we have two choices to make, whether you should use tray columns or packed columns. So when you look at these two operations, you will see that the tray column often gives rise to a larger pressure drop. Okay, so tray columns produce higher pressure drop than packed columns. This is generally true because if you look at the hydrodynamics involved in the packed column versus tray column, you see a distinct differences in the flow pattern. Okay, for example, in the tray column, each tray will have a column of liquid through which the gas will have to bubble through. Okay, at each stage, the gas bubbles through this stagnant or liquid level in the stage. So because of this, the pressure drop in the tray column is much higher. Okay, compared to, let's consider the packed column. In the packed column, we have a randomly packed or structurally packed packing material, and the gas will have to go through this packing where the resistance is coming mainly because of the packing material. Okay, the gas basically goes through the voids. And even if you do this liquid, if you send the liquid from the top for the packed column, the liquid flow rates are usually much smaller because the reflux ratio is usually smaller for vacuum distillation. So it doesn't really change the void so much. Okay, because of these differences in the flow pattern, you will see that the tray column delta P, the pressure drop, is much higher compared to for a similar operation for packed column. Okay, so now when we think about the vacuum distillation where the operating pressure itself is low, now we cannot use tray column because it offers very large pressure drop. Okay, we can put some number and see a context of this. For example, for tray column, a general rule of thumb is that the delta P per stage is roughly about 0.01 atmosphere. So this is based on looking at the design of various columns and various operations. If you look at typically per stage, what's the pressure drop? This is roughly about 0.01 atmosphere. So let's say you have a tray column that consists of 10 stages or 10 trays. Then you will see that the total delta P would be about 0.1 atmosphere, okay, because it's 10 times 0.01. Now I already told you that the vacuum distillation operates below 0.4 atmosphere, 0.4 and below. 0.4 is the kind of more like the highest limit. So if you think about the vacuum distillation operating at, let's say, even a 0.4 atmosphere and having a pressure drop of 0.1 atmosphere is quite a lot. Okay, this means the tray column operating at 0.4 atmosphere, then we are talking about delta P of the order of 25%. Okay, so 25% of pressure drop is something not physically feasible to operate. What is the case for packed column? If I do this for the packed column, you will see this delta P typically reduced by 90% of this. Okay, so delta P can be reduced by 90% of what is observed in the tray column. So what that means is delta P for packed column is roughly about 0.09 atmosphere for equivalent operation. Okay, so in this case you see this delta P is only about 2% of the total pressure. Okay, if I do a vacuum distillation at 0.4 atmosphere, the delta P, the total delta P for the packed column will only be about 2%, 2 to 3%. Okay, which is okay, which is acceptable in terms of the friction losses. So this very simple example tells you that why packed columns are more suitable candidates for doing vacuum distillation. Okay, so now you can ask, why not replace all the distillation with packed column itself if packed columns are so good? Okay, so this is a question for you to ponder about. Okay, but from now on we'll go ahead to the design of packed column. When we think about design of packed column, we think about doing it at a low pressure vacuum distillations, and we want to do vacuum distillation because we want to keep the boiling temperature small as possible. And why we want to do that is because we want to manage the heat duty, we want to look at products that are thermally sensitive, and we want to have better separation because relative volatility is higher at lower pressure. Okay, these are all the advantages. Okay, and if you look at literature, you see that the packed column distillation is often used in products like vegetable oils, fatty acids, and perfumes. Perfumes are nothing but esters of fragrant esters. So with this, let us talk about the design principle of packed column. And if you look at, I mean, as we see, the design principle is very similar to how we designed packed column for absorption and stripping. The setting up of the equations and the design calculations, they're exactly same, very similar to absorption stripping. Only key difference is in the VLE data. Okay, in the case of absorption stripping, we use Henry's law, Raoult's law, some of those empirical solubility data, whereas in the case of distillation, we have this again a very similar kind of Raoult's law, but the type of mass transfer is very different. Okay, in the case of absorption, we talk about A diffusing through non-diffusing B, whereas in distillation, A and B are counter diffusing because both components are present in both gases and liquids. Okay, but that's not the case in the case of absorption. In absorption, component A is present in both phases. Okay, only one component is diffusing. But here in distillation, both A and B are present in both vapor and liquid phase, and that basically leads to equimolar counter diffusion kind of a mass transfer. So that's one key difference that you have to take into account when we design the packed column. So here is a schematic of a packed column that can be used for distillation. You see that a lot of similarities to the tray column that we use for distillation. That means there is a condenser at the top so that the vapor can be condensed, and then part of the liquid can be sent back to the column. And then there is also reboiler at the bottom so that the vapor can be reboiled and send it back to the column. And there is also feed location to send the feed. But only difference you see is that inside the column, instead of keeping regularly spaced trays, we have a continuous packing. Okay, so from the top to bottom there is a continuous packing. Only somewhere in the middle where the feed has to be introduced, some amount of packing is removed so that there is enough space to distribute the feed. Okay, feed can be a liquid, can be vapor, it can be both, mixture of both. So whichever way you want to handle your feed, there should be enough provisions. And the packing material again is similar to what we used in absorption and stripping column. Rashing ring, interlock solids, burl saddles, etc., etc. Okay, and pressure drop calculation is also very similar to how we did in absorption. Now, if you look at the equilibrium diagram, so you can see that this is x-axis is mole fraction of A in the liquid, and y is the mole fraction of A in the vapor. The blue line here is the equilibrium line, and the black line is a 45-degree line. You can see that the distillate composition XD is the beginning of the enriching operating line, and the green line here is the feed line, Q line, and the light blue line here is the operating line for the exhausting or stripping point. And then this exhausting line cuts the 45-degree line at the residue composition XW. So XW, ZF, XD, these are all composition of the product and feed. And the Q line is the intersection of the two operating lines. Okay, and the operating lines are obtained based on McApthil method, doing mass balance, and then you will get the enriching line, operating line. Enriching operating line is based on the reflex ratio and for the exhausting line so these are the operating line that we saw in McApthil method. Same methods apply here also. But only difference is we don't do the staircase construction that we did for tray column, but we need a different approach, because here the concentrations do not change in steps like in tray column. Okay, concentration change only between one stage to another stage, but here in the packed column the concentrations of both streams, vapor as well as liquid, changes continuously from the top to bottom. Okay, so here also the top of the column above the feed line, we call it as an enriching line or enriching section, and below the feed line we call this as exhausting section or stripping section. The flow rates in the exhausting section is G bar and L bar, and like packed column absorption, the notations are also such that the parameters at the bottom of the column are denoted with a suffix 1, G1 bar, L1 bar, Y1, X1, and the top we designate with the suffix 2 to denote the top of the column. So the approach to design this packed column is to write a shell mass balance over a small thin shell of a packing, and then look at mass balance and then express mass transfer rates through mass transfer coefficients and then go about with it. Okay, so first what we will do, we will measure the height from here. Okay, so the base of the column is z equal to 0. From here onwards, first we will take the stripping section. Okay, we will do the design equation for the stripping, and after that we do for enriching. Stripping section or exhausting section, both mean the same. So here we are saying that Z from 0 to ZS. So where S stands for stripping. So we take a small width here dz, and then we write the mole balance. Okay. So since it's a continuous steady state operation, we write moles in minus moles out plus moles generated or lost is equal to 0, because it's a continuous operation, there is no accumulation here. So we are talking about a thin shell of dz Now another thing we will do is, because it's a packed column, we will denote all the molar flow rates GL in terms of moles per unit area per unit time. In the case of tray column, we dealt with only moles per unit time units. In packed column, we use per unit area basis. So these are called mass velocities, okay, gas mass velocity or liquid mass velocity in the units of moles per unit area per unit time. This unit area refers to the cross-sectional area of an unpacked column. So with that, we can write that what is coming in is Gy at Z, Gya minus Gya at Z plus dz, and in the bottom of the column it is a stripping operation. So what it means is that A is removed from the liquid to the vapor. That's what stripping means. Okay. So we write Na A dz. So here this A here is the interfacial area per unit volume of packing. Interfacial area per unit volume of So you can look at this equation exactly what we used for absorption and stripping before, where A here is the cross sectional area of the unpacked column, that's an empty column. So rearranging this equation, we see that Gy at Z plus dz minus Gy at Z by dz is equal to Na times A. So the left hand side can be written as d by dz of Gy, that is equal to Na. This Na here is Ky prime Yi minus Y times A. See, I am using Ky prime because this is for equimolar diffusion. The mass transfer coefficient notations are different for A diffusing through non-diffusing B or equimolar counter diffusion. So the prime number here, the prime here notes that this is a equimolar diffusion kind of a problem. Okay, this is important because when you calculate the mass transfer coefficient from correlations, you have to see whether this correlation is applicable for equimolar or A diffusing through non-diffusing B. Okay, the type of mass transfer is important. Okay, so now we can rewrite this and integrate. So the integration of this equation is only for the bottom of the column. So Z goes from 0 to ZS, okay, that's the part of the exhausting section, and correspondingly the composition of A goes from Y1 to YF is actually somewhere here, okay. This is basically the limits of the exhausting line, operating line, okay. So it starts at Y1, sorry, at this Y1 is somewhere, yeah, Y1 is here, and from here to this point, which is the YF, this is YF. So you can identify the composition at the just above the feed line. And then the right hand side, we have the molar flow rate G and Ky. They can be a function of the composition, or like we assumed before, the combination of G by Ky prime A, this can be considered to be constant, and we call this as HTG. This is height transfer unit. So therefore, we find that ZS, that is the height of the stripping column, is equal to some HTG times integral dy by yi minus y, going from y1 to yf. We in fact did one problem in absorption of this kind, where we obtain the interfacial concentration and do the integral, and in this kind of distillation column also we do the same thing. What we do is, for any point along the exhausting line x comma y, we find the ratio of kx with ky. Those are the kx prime and ky prime, those are the mass transfer coefficient ratios, and that will intersect the, suppose for the exhausting line, if I start from here, I need to know the slope. The slope is nothing but minus kx prime by ky prime, and so we choose several points along the operating line and then draw these lines, and those will give you xi and yi. Those are the interfacial concentrations, okay. So we read xi from here and the corresponding, we read the yi value from here, and this is the corresponding y value. So this is the concentration difference that goes in the integral, and we generate many such x comma y points on the operating line, and correspondingly get the equilibrium compositions, and that gives the driving force here, okay. So what it means is, we have to plot 1 over yi minus y versus y, and then you basically have this integral going from y1 to yf. So that is this value. We can also write this is HTG times NTG, and NTG is this integral. Now generally in distillation, you can see that the operating line, the equilibrium line has a changing slope, okay. It's continuously changes from the pure A to pure B, okay. But you may remember that in the case of absorption, if this equilibrium line slope is constant, we can use overall driving force instead of interfacial driving force. But this is not very much applicable in distillation. But suppose if the distillation is happening over a small range of composition, and in that composition range, if the slope is constant, then we can write in terms of overall driving force. Some of the problems I solved in the class, we did I think batch distillation, where we had a similar kind of integral, and we used to approximate the equilibrium line to a straight line for a very narrow range of concentrations, okay. Suppose if you do continuous vacuum distillation in those ranges, we can approximate y as a linear, the equilibrium line as a straight line. So in those cases, it makes sense to define the overall NTOG. For the same limit, we can replace the interfacial concentration with the equilibrium concentration. and similarly HTOG can be written as HTG plus HTL by M. So total column height ZS can be written as HTOG times NTOG. So this is valid only if equilibrium line has a constant slope, which is M here, mg by L. This is the same expression that we used in absorption also. So if you look at this exhausting section, it is it's straightforward like we did before. And now what we need to do from ZS to the top of the column, that is enriching section. So we have to write set of equations for the enriching line also, because the operating line is different. Okay, for the exhausting line, the operating line is this light blue line, but then when we did this, when we do this enriching section, the operating line has to be the red line. Okay, so that distinction has to be made. So now we do enriching section design. So again we take a small shell dz. So here we write this equation from Zs to we will say Zt, that is the total length. So this is a range of enriching section. So here again we can write the material balance or mole balance. So here is a small caveat. In the enriching section, what is happening is B is absorbed. Okay, so in the enriching section, B is absorbed. So we have to write this equation as if for B it is an absorption. But at the same time, this is an equimolar counter diffusion. Okay, if B is diffusing from vapor to liquid, equal moles of A will diffuse in the opposite direction. That's what equimolar counter diffusion means. Okay, so if I have to draw, this is an interface. If I look at a small section of liquid vapor interface, you will see that the composition for B, this is YB bulk and this is YB at the interface and this is XB at the interface and this is XB at the bulk. Okay. Now B diffuses from vapor to liquid. Now in response to this, A will counter diffuse from liquid to vapor. So if I have to draw the composition for X, this is XA bulk and this is XAI interfacial concentration, and then there will be a interfacial concentration on the vapor phase because of the equilibrium setup, and this would be the composition of A in the bulk. So here A is diffusing from liquid to vapor. Okay, so we have to recognize that when we write the Na for this mole balance. So this mole balance is written for species A, but when we say it's absorption, we said it is absorption with respect to B, but it also means that A is counter diffusing. Okay, this is a very important aspect which we did not discuss in the case of absorption, because there only one component was diffusing, not the other. But in distillation, both are diffusing on both ways. Okay, so that has to be taken into account. Okay, so we will rewrite this. So Gy at Z plus dz so here we write this is Na is equal to Ky prime Yi minus Y. So here I am dropping suffix A because we know that this is with respect to species A, and here we used a suffix A and B because we want to distinguish between those two. So there is A here, and then from here you can show that d by dz of Gy is equal to Ky prime So let me also make a small correction here. In the stripping section, we use this G bar here because the gas flow rate, vapor flow rates are different in the two sections, and here the limit should be YF to Y1. So using overall driving forces, we can write NTOG as from YF to Y1 dy by Y star minus Y. And HTOG as HTG plus mg by L or ml by G. G by L. Y2, yeah, Y2, yes. Thanks for pointing that out. Yeah, this should be Y2. So the total column height ZT is ZS plus ZE, and this is something we wrote as HTG times NTG for the stripping section plus HTG times NTG at the enriching section. And column diameter can be obtained from pressure drop calculations. Column diameter is to be obtained from pressure drop calculations. Okay, that's all.